Hello, welcome back to General Chemistry 1. My name is Daniel, and in this video we're going to be looking at bonding in terms of orbitals. So far we've been looking at bonding in the form of localized electrons surrounding atoms, whether they be in bonding or lone pair electrons. Now we're going to take a look at bonding from the perspective of the orbitals in which those electrons are occurring in. So we're going to do that, and then we're also going to look at the applications in molecular orbital theory and molecular orbital energy diagrams. So first off, let's talk about the bonding between atoms. So we know that in single atoms we have, s bonds, p bonds, s orbitals, p orbitals, so on and so forth, like we have here. And p orbitals, for example, have these dumbbell-based shapes. So the question then is, how do these orbitals interact and overlap in order to form bonds? So let's look at an example molecule. Let's look at methane. So carbon, as we know, has 3 different p orbitals. So it would look something like this. It has one in that direction, one in that direction, and then one kind of in the page, out of the page. So wouldn't we expect methane, which is just carbons bonded to hydrogens, to look like something on the left here? Since there's 3 p orbitals, we'd expect that there would be 3 hydrogens bound to it at different 90-degree angles, as these are at. However, in reality, we see that carbon is in fact a tetrahedral molecule. So it has 4 different bonds at about 109.5 degrees. So how did we get from the what we'd expect from single carbon atom with its p orbitals to the structure on the right? So let's look at the free orbitals in carbon. Carbon has 1s, 2s, and 3 2p orbitals. So we have to look at the valence electrons when we're talking about bonding. So we're not going to really consider the 1s orbital for bonding. So then for bonding we have 2s, 2p, 2y, 2py, and 2pz. So how do these interact to form those 4 bonds? It's done through a process known as hybridization. Basically what happens is that in order to form the 4 bonds required in methane, the carbon's 2s and 2p orbitals are going to interact to form these hybridized orbitals, known as sp3 orbitals. So it's going to interact to form these, and you form a total of, as we see, 4 different kinds of bonds in these sp3 orbitals. We just add up the exponents here, and that's a total of 4. So that's how methane gets its characteristic shape, through the hybridization of 2s and 2p orbitals. And these form sp3 orbitals, which have partial s and partial p character. So we see that's how the bonding happened. Let's look at bonding in some different other compounds and their hybridizations. So, for example, if we have something like BeCl2, that's going to be sp hybridized. So we take the 2 s electrons, the 2 electrons being from beryllium, and what happens then is that the electrons go into these sp hybridized orbitals, leaving 2 empty lone pair, or 2 empty 2p orbitals. In something like BF3, this has 3 bonds, so it's going to be sp2 hybridized. So we take the 3 electrons from boron, and they go into 3 sp2 hybridized orbitals. And then finally, as we saw for methane, methane is sp3. Carbon has 4 valence electrons in it. So the 2s and the 2p electrons are all going to go into 4 separate sp3 orbitals. So how can we know which hybridization is present in each kind of molecule that we encounter? It's solely going to be based on the effective electron pairs around the central atom. Meaning, for example, we can look at the electron coordination in order to look at hybridization. So any kind of linear molecule, any kind of species with an electron coordination that's linear, that's going to be sp hybridized. Anything trigonal planar is going to be sp2 hybridized. Anything with a tetrahedral electron coordination is going to be sp3, and so on and so forth. When we get into trigonal bipyramidal and octahedral, we add just a d or a d2 to the front of that. And you want to remember that electron coordination, that's just the number of bonding electrons plus the number of lone electrons on our central atom. So for example, something like water with 2 lone pair electrons here has 1, 2, 3, 4. It has a 4 effective electron pairs. So it would be tetrahedral and sp3 hybridized. Okay, so the important thing then is we can see that the hybridization, the sum of the exponents, is going to equal how many effective electron pairs there are. So for example, in sp3, we have 4 electron pairs, and we have a 1 over here, plus that 3 means 4. So sum of the exponents in each hybridization displays how many are involved in bonding. And we see the relationship between that in this table here. We could also look at, for 6 effective electron pairs, we'd have D2 plus 1s plus 3p would give us a total of 6. So you're just adding up the exponents like that. And so it's going to be important that you be able to identify the hybridization that's going on in each kind of atom within a molecule, or within a molecule if it has one lone central atom. And we'll get into some of those questions in the workshop. For now, let's go into double bonds and triple bonds. So what happens when we form double bonds and triple bonds, so far we've only been talking about single bonds, is that we form 2 sets of bonds. We also have sigma bonds, which are bonding orbitals within the planes of the atoms. So that's something like this. We see that sp3 orbital in green is within the plane between the 2 atoms. What we can also get is what's called pi bonds. And pi bonds are formed by the lobes of the p orbitals. So we see that they're occurring above and below the planes of the atoms. And that's just because of the interactions of the p orbitals above or sideways from the actual carbon atom itself. So what the basic rule for this then is going to be is that in a single bond we have 1 sigma bond. In a double bond we have a sigma bond and we have a pi bond. And then finally in a triple bond we have 1 sigma bond and 2 pi bonds. So the important thing we're going to have to be able to do with this is be able to count up in a molecule how many of each bond there is. How many sigma bonds, how many pi bonds. That's going to be the predominant important thing we're going to do with this. So let's take a look at an example molecule. See if you can count up how many sigma bonds and pi bonds there are in this molecule. And remember that every bond has a sigma bond, but then double triple bonds add in 1 and 2 pi bonds respectively. Okay, let's count. So let's first see how many bonds total we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then there's a bond here too, so that's 17. So we have 17 sigma bonds total. Now we have to count up the pi bonds. We'll do that in red. So we're just looking for anywhere there's a double or triple bond. We see 1 pi bond here and 2 pi bonds, or another pi bond over here between carbon and oxygen. So there's only going to be 2 pi bonds in this molecule for a total of 17 sigma bonds and 2 pi bonds. What you can also do is for sigma bonds, you can just take the atoms minus 1. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 atoms. Minus 1 is our 17 sigma bonds. If you want to count or if you want to use that rule, either or works. But for pi bonds, you still have to count up how many double bonds, triple bonds there are, and assign pi bonds numbers to each. We'll see more of this in the workshop as well. For now, we're going to change gears and go into molecular orbital theory. So as I said, previously with Lewis structures, we've been talking about just a localized electron model. That means we're assigning electrons to atoms. We're looking at whether they're bonding electron pairs or lone pair electrons. But it falls short in describing systems with unpaired electrons.